Hello everyone, hope you are doing very well. Today, as you all know, that we are going to cover some previous year questions that has been there in our JEE examinations. So let's begin today's topic. NCERT Chapter 5 Coordination Compounds JEE PYQs. This is disclaimer. The objective of today's lecture, so after attending this lecture, you will be able to solve competitive level questions of the coordination compounds chapter. And the topic that we are going to cover, we are going to focus mainly on the JEE PYQs. That means we are going to practice the JEE previous year questions. So let's begin with our first question, which is a JEE PYQ, and it is covering the NCERT section 5.2. Question is, yellow compound of lead chromate gets dissolved on treatment with hot NaOH solution. The product of lead formed is a. So question is saying that a yellow compound of lead chromate, when dissolved, when it is treated with hot sodium hydroxide solution, and you have to tell that what is the product of lead that you are going to obtain from this process when you are dissolving a yellow compound of lead chromate after the treatment of sodium hydroxide with it. Okay, so you have to know the name of the, or you can say from the options you have to choose the product that you are going to form for lead. The options are tetra-anionic complex with coordination number 6, neutral complex with coordination number 4, dia-anionic complex with coordination number 6, or dia-anionic complex with coordination number 4. So you have to tell that which is the product that you are getting from this reaction of yellow compound lead chromate and hot sodium hydroxide solution. So you have given some time, try to solve this question, and then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option D, dia-anionic complex with the coordination number 4. This is what the product that you are going to obtain. Lead chromate's nature. So if you talk about the lead chromate nature, it is a yellow compound that is only slightly soluble in water. So lead chromate, that is PbCrO4, is a yellow compound and it is only slightly soluble in the water, not the completely soluble. When it reacts with sodium hydroxide, it forms a complex after the reaction. Chemical equation. So the overall reaction can be represented as lead chromate PbCrO4 plus 4 NaOH, that is 4 molecules of sodium hydroxide. After heating, we are getting a complex of sodium tetrahydroxoplumbate second, where you can see this is the formula of the complex Na2PbOH whole 4 plus Na2CrO4. Okay, so this is a complex that you are getting when you are reacting the yellow compound of lead chromate in hot sodium hydroxide solution. Okay, so you are getting this complex named sodium tetrahydroxoplumbate second. The product identification. So you have to identify the product, right, that you are obtaining of lead. So lead containing product formed is a tetrahydroxoplumbate second ion, which is PbOH whole 4 2 negative. right? So this complex, if you dissolve it in water, you will get two cations of sodium positive and one anion of this PbOH whole 4 2 negative, right? After the removal of 2 Na2, you will get 2 negative charge on this ion, and you will get a tetrahydroxoplumbate ion, that is lead containing product, which is this PbOH whole 4 2 negative. And the charge on this like complex is basically -2, right? It has a charge of -2, so we can say this is dianionic complex. First of all, anionic because negative charge and negative in 2 magnitude, so the charge will be dianionic. Okay, so this is a dianionic complex we are getting. And the coordination number for this complex, the coordination number is 4, because 4 hydroxyl group are directly attaching with the central metal ion, that is lead here. So coordination number is 4. So 4 hydroxide ligands are bonded to lead. That means coordination number will be corresponding to 4 and the charge will be -2. So it is a dianionic complex. Hence, our correct answer regarding the product of lead that we are forming is dianionic complex with coordination number 4. Let's move to our next question. So this is a JEE PYQ and this is covering the NCERT section 5.7. Question is, the mismatched combinations are. So we have given some combinations from A to E, like A, B, C, D, E. We have given some combinations. You have to tell the mismatch combination. That means the combination that is not matching correctly, right? So A is chlorophyll is matching with cobalt. B is water hardness is here given as a match with EDTA. C is photography, which is given as a match with AgCN whole twice, whole negative complex anion. D is given as Wilkinson catalyst as a match with PH3P whole thrice RHCl complex. Similarly, the E is given as chelating ligand and the match of it is given as D-penicillamine, right? So these are the 5 combinations that are given. You have to select the mismatched combinations. So choose the correct answer from the options given below. Options are A and C only, A and E only, D and E only, or A, C and E only. So you have given some time, try to analyze this question and then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option A, that is A and C only. That means the mismatch combination is present in A and C only. So let's talk about one by one. So A is given as chlorophyll and cobalt, right? If you talk about the combination, it is a mismatch combination because chlorophyll central metal atom is magnesium, not cobalt. Okay, so in the structure of the chlorophyll, the central metal is actually magnesium, Mg, not the cobalt. So this is a mismatch. And the correction should be that cobalt is found in the vitamin B12. Basically, cobalt should be matched with the vitamin B12 because cobalt is found in the vitamin B12. And in the chlorophyll, the central metal atom of the chlorophyll is actually magnesium. Okay, so this is a one mismatch combination, that is A. Let's look at another one. So B is given as water hardness and its match is given as EDTA. So it is a match combination. It is a matched combination because EDTA is used to estimate and remove the water hardness. Okay, so water hardness is a thing which is in which we use the EDTA especially to estimate the water hardness and to remove it also. The method how we do this process, simply you have to titrate with sodium EDTA, Na2 EDTA complex. Okay, so when you do the titration with Na2 EDTA, this process carrying on. The mechanism, so calcium 2 positive, magnesium positive, which is responsible for the water hardness. So calcium 2 positive and magnesium 2 positive ions, which are causing hardness, form a stable complex with EDTA. Okay, so what we do, we take water, and we have to titrate it with Na2 EDTA. So these calcium 2 positive and magnesium 2 positive, which is actually present in the water, due to which they are causing the water hardness, they are reacting, or they are forming, or they are able to form stable complexes with this EDTA. Okay, so when you titrate it, the calcium 2 positive and magnesium 2 positive, which are causing the hardness of the water, they form complex, stable complex with EDTA, and the water hardness gets removed. Selectivity. So selective estimation of calcium 2 positive and magnesium 2 positive is possible due to the difference in the stability constant of calcium and magnesium complexes. Now both the ions which are present in the water, calcium 2 positive and magnesium 2 positive, they have their difference in their stability constant of their complexes. Okay, so there is difference between their stability constant of their complexes, due to which we can selectively estimate the calcium 2 positive and the magnesium 2 positive. So it is selective estimation of these two ions is possible due to this difference in their stability constant of their complexes, the calcium and the magnesium complexes. Okay, so B is a matched combination, but we have to identify the mismatched one, and until now we have find out the A, which is a mismatched one. Now let's see the C part, that is photography, which is here giving as a match with AgCN whole twice whole negative complex anion. This is a mismatch combination. Okay, basically complex which is used in photographic fixing is not this complex, AgCN whole twice whole negative. The correction should be here that sodium thiosulfate is used, which is forming the complex AgS2O3 whole twice whole 3 negative, and the fixing process is that the developed film is going to be fixed by washing it with hypo solution, or you can say sodium thiosulfate solution. So we don't use this complex, and this or you can say this complex anion given as a match with the photography. This is not actually we use in the photographic fixing. Actually we use the sodium thiosulfate, which forms this another silver complex, that is silver S2O3 whole twice whole 3 negative, and then the fixing process involves basically that film that is going to be made, that you have to fix, that is fixed by washing with sodium thiosulfate solution. The mechanism, so this hypo solution dissolves undecomposed silver bromide by forming a soluble complex ion, that is silver S2O3 whole twice whole 3 negative. So when you wash this film, developed film, okay, after like after fixing with the hypo solution, this hypo solution dissolves the undecomposed silver bromide by forming a soluble complex ion, which is AgS2O3 whole twice whole 3 negative. So we are using this complex which is forming after the reaction of hypo solution, right, like sodium thiosulfate, and this silver bromide, and we are not using this given complex anion, that is AgCN whole twice whole negative, right? So that is why this is a mismatched. The reaction follows is silver bromide, which is undecomposed, it is going to be dissolved into the hypo solution when you are washing the developed film. 2s2o3 2 negative, and then this is going to form this complex of silver AgS2O3 whole twice whole 3 negative, and you got bromide ion. Okay, so this is how you done the fixing in the photographic. So this is a mismatched combination. Okay, so until now A and C are the one that are mismatched, right? The B was the matched combination. Now let's see the D1. So it is given as Wilkinson catalyst, and it is given a match with PH3P whole thrice RHCl complex, rhodium complex, right? So this is a structure of Wilkinson catalyst. If you see, we have rhodium at the very center, and it is connecting with 3 triaphenyl phosphine ligands and 1 chloride ligand, right? So this is a structure of Wilkinson catalyst, and it is a matched combination because you can see this structure and this given complex, or you can say complex formula, is same, right? Rhodium as a central metal ion, 3 triaphenyl phosphine as a ligand, and 1 chloride as a ligand, right? And this is what the structure is already given here. So they both, the complex and the structure, are same of Wilkinson catalyst. So this is a matched combination. The formula correctly represents the Wilkinson's catalyst. Lastly, let's see its function. So basically, Wilkinson catalyst is a homogeneous hydrogenation catalyst. That means we used it for the hydrogenation of alkenes. Alkenes means the hydrocarbons, or you can say unsaturated hydrocarbons having double bond between the 2 carbons. So first of all, we add the hydrogen to the double bond to get converted into the alkanes. Okay, the example include hydrogenation of 1-hexene to N-hexane. Okay, 1-hexene means one double bond is present between 2 carbon in the 6 carbons chain, and when you do the hydrogenation using the Wilkinson's catalyst, the 1-hexene converts to N-hexane. That means a single bonded carbon chain. So this is the reaction, that CH3, CH2, 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 CH, double bond CH2. This is 1-hexene. At the first position, we are placing a double bond and 6 carbon are present. When you are doing hydrogenation, that means adding hydrogen in the presence of Wilkinson's catalyst to the 1-hexene, it is converting to N-hexane. That means all the carbon, or you can say 6 carbon chain, having single bond between them. So this is like D is also a matched combination. Wilkinson catalyst formula is correctly given. So finally, let's see the E1. E is chelating ligand and giving it as a match with D-penicillamine. This is the structure of penicillamine, where you can see we have the COOH group, CNH2 group, and this is SH group, right? Connecting with the C and 2 methyls are also there. So this is a match combination. Why? D-penicillamine act as a chelating ligand. Chelating ligand, what is chelating ligand? So we have studied about this, that chelating ligand is the one which stabilize the structure of the complex after developing a ring-like structure after forming more than one bond with the central metal ion at the same time in the complex, right? So D-penicillamine is actually act as a chelating ligand. So this is also a matched combination. And if you want to know more, chelating ability stems from its thiol, amine and carboxylic groups. So what are the groups, what are the donor atoms that are going to be there in the D-penicillamine that is going to build its chelating effect? So its chelating ability is from its thiol, that is SH, amine, that is NH2, and the carboxylic acid, that is COH groups, that is attached in the D-penicillamine. Remember, we have seen the structure where all these groups are present and they both can form the bond with the central metal ion in a complex, forming a ring-like structure around the central metal ion, stabilizing the complex. Okay, so this D-penicillamine chelating ability is from these 3 groups, and they form a stable complex with heavy metal ions like copper. Okay, so D-penicillamine is generally form stable complex with heavy metal ions. It is used in treating the conditions such as Wilson's disease, and its application is it is used to remove heavy metals from the body. So this is the extra information that we have provided for the D-penicillamine ligand. Okay, so this is also a correct match. The E1 is also a correct match. So only the incorrect match or mismatched combination is given in A and C, the chlorophyll cobalt and photography and this AGCN whole twice whole negative, right? So A and C only is our correct answer. Okay, let's move to our next question. This is a JEE PYQ and this is covering the NCERT section 5.5.4. Question is, transition metal complex with highest value of crystal field splitting, that is delta naught, will be. So you have to tell that which transition metal complex is having highest value of CFS, that is crystal field splitting delta naught. Okay, so from the given options you have to choose. The options are chromium H2O whole 6 whole 3 positive, molybdenum H2O whole 6 whole 3 positive, iron H2O whole 6 whole 3 positive, or osmium H2O whole 6 whole 3 positive. So you have to select the one complex or transition metal complex that is having the highest value of crystal field splitting. Okay, there are many factors that you can observe regarding the crystal field splitting of these complex and that you have to consider here. Okay, so you have given some time, try to solve this question and then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option D, that is osmium H2O whole 6 whole 3 positive. So what are the factors that we are going to focus on which is affecting the crystal field splitting energy for any octahedral complex? First step is the nature of ligand. How is the nature of ligand is? So basically either it is a strong field or a weak field. So strong field ligands cause greater splitting than the weak field ligand. This we all know, right? That ligand field strength is very important because it is going to tell us that how well a ligand interact with the metal ion to split the energy of d orbital of metals, right? And the strong field ligands cause larger energy gap between the splitted d orbitals, so it will cause greater splitting than the weak field ligands. All the given options have H2 as the ligand, so we can't focus on this factor. Why? Because all the options have same ligand given, all the complex have same ligand given, that is water. So water is a neutral ligand, we all know. We can't go with this, the nature of ligand factor. So H2 is a neutral ligand with charge 0. Step 2, that means the another factor we can observe is oxidation state of metal ion. So higher oxidation states lead to greater delta naught. Okay, so if the metal ion is having higher oxidation state, that means more splitting, that means greater crystal field splitting, that is delta naught value, right? So oxidation state of metal in the given complex are, we have given complex, first is chromium. The metal ion is chromium in the complex, chromium H2 whole 6 whole 3 positive. The oxidation state of chromium in this complex is +3 because water is a neutral ligand, right? It is having charge 0. So 6 times 0, that means 0. So the overall charge on the complex will become the oxidation state of the central metal, that is chromium, right? So the oxidation state of chromium become +3. Second complex is given as for molybdenum H2O whole 6 whole 3 positive. Here comes the same case that H2O is a neutral ligand having charge 0. So the overall charge on the complex becomes the oxidation state of central metal, that is molybdenum. So molybdenum oxidation state is +3. Iron in this complex is having again +3 oxidation state due to the same reason. And similarly, the last complex, that is osmium H2 whole 6 whole 3 positive. Then osmium is also having in this complex as +3 the oxidation state because of the same reason. So after looking at the ligand and the oxidation state of central metal atom, they all are same in given 4 complexes, right? Now we have to find another factor. Step 3 includes the factor metal's position in the periodic table, that is D series. Okay, we are talking about D series. So delta naught is increasing significantly down a group in the transition series. D series include 3D series, 4D series and 5D series, right? And why 3D, 4D, 5D? Because the last electron will fill into respective orbitals like 3D, 4D and 5D. So it is observing that delta naught value increases down a group significantly in transition series. If you move from 3D to 4D to 5D, the delta naught increases. So let's see the order. The order will be highest delta naught will be for 5D, then for 4D and then for 3D. So delta naught, that means higher crystal field splitting will be observed in the octahedral complex of 5D series, then 4D series and then 3D series. Let's analyze the options one by one. So this first complex, that is chromium H2O whole 6 whole 3 positive, it is having a 3D metal complex because this is a chromium complex which is a 3D metal. Okay. Now the second complex, that is molybdenum H2O whole 6 whole 3 positive, this is a 4D metal complex. So molybdenum is a 4D metal. Next complex, osmium H2O whole 6 whole 3 positive, this is a 5D metal complex. Osmium is a 5D metal. And here in this complex, iron H2O whole 6 whole 3 positive, this complex is a 3D metal complex. That means iron is existing in the 3D series, in the 3D transition series. Okay, so chromium is in 3D series, molybdenum is in 4D series, osmium is in 5D series and iron existing in 3D series. And what we have known? We have known that the crystal field splitting will be largest, or crystal field splitting will increase when you go down a group in the transition series. What does mean? What does it mean? That the complex which is having a 5D metal in it, that is going to be have the largest value or the highest value of crystal field splitting, right? So here conclusion is that delta naught is increasing significantly from 3D series to 4D series to 5D series metals, right? That means highest will be observed in the octahedral complexes by the 5D series metals, then 4D series metals and then 3D series metal. So complex with a 5D metal ion will have the highest crystal field splitting value, and we have therefore this complex osmium H2O whole 6 whole 3 positive, which is a 5D metal complex because osmium is a 5D metal, 5D series metal. So this complex will have highest value of crystal field splitting, that is delta naught. Okay, so how we solve this question? Basically we have to observe the factors that are affecting the value of CFSE for the complexes in the octahedral geometry, right? And then we have to we have seen that the ligands are same, the oxidation state of metal ion is same in all the complexes given. Now the third is the delta naught value with the existence of the transition series metal. Okay, so in which series the transition metal is existing. So down a group, delta naught increases in the transition series. So using that fact, we have concluded that the osmium H2O whole 6 whole 3 positive, which is a 5D metal complex, because osmium is a 5D series metal, this complex is going to have highest value of crystal field splitting. Okay. Let's move to our next question. This is a JEE PYQ and this is covering the NCERT section 5.6. Question is, in the cobalt carbonyl complex, that is CO2CO whole 8, the number of cobalt-cobalt bonds is X and terminal carbonyl ligands is Y. X plus Y equals to what? Okay, so you have to tell, we have first of all given a cobalt carbonyl complex, that is this one, CO2CO whole 8, right? The number of cobalt-cobalt direct bond is X, and you have also given that the terminal carbonyl present in this structure of complex is Y. You have to tell the value of X plus Y. You can simply draw the diagram of complex and then you can determine the value of X and Y and X plus Y. So you have given some time, try to solve this question and then we will see the correct answer. Okay, let's see. So for this question, first of all, let's see the given thing. So we have given the cobalt-cobalt direct bond is X and the terminal carbonyl ligands present is Y. If you see the structure of this complex CO2CO whole 8, this is the structure and you can see that two cobalts are bonding together directly, and at each cobalt we have 3 number of terminal carbonyls present as ligand, and also 2 ligands are present which are bonding, 2 ligands of carbonyl are present which are bonding with both the cobalt, right? So we are calling these carbonyl as bridging carbonyl, okay, because they are bridging these like these two cobalts, right? And these pink one are terminal carbonyls, okay, because they are present at the corner of the structure, or at each cobalt we have this terminal carbonyl, 3 at each, right? So the terminal carbonyl ligands, which is 3 on each cobalt atom, will be equals to Y, right? Which is equals to 2 times 3, because there are 2 cobalt and 3 carbonyl or 3 terminal carbonyl are present at each cobalt. So 2 times 3 is equals to 6. So Y is 6. And similarly, the direct metal that is cobalt-cobalt bond is X and it is 1. You can see the structure, right? So Y is 6 and X is 1. What we have to determine? The value of X plus Y. So X plus Y is, which is total bonds, is equals to X is 1, Y is 6. So 1 plus 6 is 7. So our answer will be 7. Okay. Let's move to our next question. This is a JEE PYQ and this is covering the NCERT section 5.3.2. Question is, the IUPAC name of the complex platinum ammonia whole twice chloride NH2CH3 whole thrice chloride. So you have given this complex formula. You have to tell the IUPAC name of this complex. Options are diamine chlorido, methanamine platinum second chloride, diamine methanamine chlorido platinum second chloride, diamine chlorido aminomethane platinum second chloride, or bisamine methanamine chlorido platinum second chloride. These are the 4 options. You have to select the correct IUPAC name. You have given some time, try to solve this question and then we will see the correct answer. Okay, let's see. So for this question, the correct answer is option A, that is diamine chlorido methanamine platinum second chloride. Let's see the steps for IUPAC nomenclature. First of all, you have to know the cation part of the complex, which is platinum ammonia whole twice, chloride, NH2CH3, that is methanamine whole positive, because there is chlorine which is counter anion, which when go uh, gives us a one positive charge at this complex, right? So we got this cation, and the anion is chloride, right? It is present at the outside of the coordination entity, that is this chloride ion, counter ion. Okay. After this, you have to know the ligands and their name. So ammonia is given, which is a neutral ligand, which is named as amine. Also, chloride ion, which is an anionic ligand, so we name it as chlorido. O, we are putting O at the end because it is an anionic ligand. And we have NH2CH3, which is a neutral ligand, so its name will be methanamine as it is. Let's see the number of ligands now. We have two ammonia ligands, so we call it as diamine. We have one chloride ligand, so we call it as chlorido. And we have one NH2CH3 ligand, so we call it as methanamine. Another step is order of ligands. So we have to arrange the order of the ligands alphabetically so we can write the name. So ligands are named in alphabetical order. Amine will come first because it has A in the first position. So amines from NH3 will come first. Chlorido from Cl negative will come second. And methanamine from NH2CH3 will come third. Ligands order will be diamine, chlorido, methanamine. So we don't count here dia, which is representing the number of ammonia in the alphabetical order. Okay, we always count from the, or we always consider the name, first letter of name of ligand. So amine we consider because A is the first one. So that's why we are writing here diamine, chlorido, methanamine. So this is the ligand order. Now the central metal atom. Central metal atom is actually platinum, PT, already given, right? It's because it is a cationic complex, so metal names will remain unchanged. Okay, so complex ion is cation, so metal name will remain as it is, that is platinum. And the oxidation state of platinum, that you have to write in the Roman numeral. So for finding it, let the oxidation state of platinum be X. So platinum has X oxidation state plus twice of 0 because ammonia is a neutral ligand, plus 1 times -1 because chloride is an anionic ligand having -1 charge, and plus 1 times 0 because NH2CH3 is a neutral ligand. This is equals to +1, which is the charge on overall this cationic complex. When you solve it, it will be X. This becomes 0, this becomes 0, and this 1 times -1 will become -1. So X minus 1 equals to +1. This -1 will go in the right hand side. X become equals to +2. That means the charge on the platinum or oxidation state of platinum is +2. So we put it all together for the cation, and we get we combine the ligand names in alphabetical order along with the, or followed by the metal name and its oxidation state in the Roman numeral. So we get the name as diamine chlorido methanamine platinum 2. So this is the cation part. Okay, we are putting everything together for the cation part. Now for the name of the cation and the anion, we just combine the name of the cation and the anion to get the complex name. So it will be diamine chlorido methanamine platinum second chloride. The cation name will come first and the anion name will come second. So we combine the names of cation and anion and we got the name of our complex as diamine chlorido methanamine platinum second chloride. Okay. Okay, let's move to our next question. This is a JEE PYQ and this is covering the NCERT section 5.5.4. Question is, the degenerate orbitals of chromium H2O whole 6 whole 3 positive are. So for this complex, you have to tell the degenerate orbitals. From the options are dxz and dyz, dyz and dz square, dz square and dxz, or dx square minus y square and dxy. So you have given some time. Try to solve this question and then we will see the correct answer. Okay, let's see. So for this question, the correct answer is option A, dxz and dyz. This complex, that is chromium H2O whole 6 whole 3 positive, is an octahedral complex. Okay, so we have to consider the degenerate orbitals of octahedral complex. This is a figure representing the octahedral crystalline field where we have this metal d orbitals, dx square minus y square, dz square, dxy, dxz and dyz, the 5 metal d orbitals which are in degenerate form, having equal or same energy. Okay, this is in the case of free metal ion when the metal ion is free. This a slight energy increase in the metal d orbitals, but still they are degenerate, and this slight increase is due to the average due to the formation of the spherical crystal field, symmetrical spherical crystal field around the metal ion. So there is this average energy. This is the representation of average energy of d orbitals in the spherical crystal field. Okay, now splitting happens. Okay, so these 5 degenerate orbitals, or you can say these 5 d orbitals which are degenerate, splitted into 2 non-degenerate energy levels. Higher one is called the EG level, having dx square minus y square and dz square orbitals. The lower energy level is T2G, having dxy, dxz and dyz d orbitals. So splitting of d orbitals in the octahedral crystal fields follows this thing that they degenerate into the 2 energy levels. First is higher one is EG, lower one is T2G. Okay, delta naught here is representing the energy, which is total energy that is splitting these 2 energy levels in the higher and the lower states. Okay, and barycenter here, so crystal field splitting is such that the total energy lowering of the T2G set due to stabilization is exactly compensated by the total energy increase of EG set due to destabilization. Okay, so this will ensure that the overall average energy of the d orbitals at the barycenter remains unchanged. Okay, so this is what is barycenter, and the energy which is raised for the EG level is 3/5 of delta naught, and which is lowered for T2G is minus 2/5 delta naught. Okay, and this is the degeneration happens when there is a formation of the complex and ligand will attack towards the metal ion and form the bond with it. Okay, so basically this is the figure showing the octahedral crystal field splitting, and you can clearly see that we are talking about the octahedral complex, right? So we have also seen that splitting of d orbital is happening into the 2 sets of non-degenerate orbitals, the higher energy level EG level and the lower energy level T2G level. Okay, where 3 orbitals of d are present, and in the EG 2 orbitals of d are present. We have to identify the degenerate orbitals of this complex. So chromium here is in +3 oxidation state, so these electrons will occupy the lower energy level according to the rule, that is T2G orbitals. Okay, so chromium is in +3 oxidation state here, because you can see that the water molecule is a neutral ligand, right? So water molecule is a neutral ligand, that means its charge is will be 0, right? So the overall charge on this complex is going to be present, or it's going to be present on the charge of the central, or it is going to be equal to the charge of the central metal atom, that is chromium, right? So the chromium 3 positive, chromium is in +3 oxidation state, that means its electronic configuration become D3, okay, argon D3. So these 3 electrons will occupy the lower energy T2G orbitals, T2G3D orbitals, one by one. So degenerate orbitals of chromium H2O whole 6 3 positive will be the T2G set, which is DXY, DYZ and DXZ. Each electron of chromium 3 positive will occupy each d orbital in the T2G set according to the Hund's rule, right? And the another set is EG set, having dx square minus y square and dz square orbitals, d orbitals, but they are at higher energy level than T2G, and the electron will not consider to fill in these d orbitals. They will only fill in this T2G set for this complex, right? So that's why our correct answer is option A, that is dxz and dyz. Okay. Okay. Okay, thank you so much. That's all for today's chemistry session. Thank you.